Welcome everyone. This video is going to be on section 11.6. The section is called Absolute Convergence and the ratio and root tests. Okay. So given a series, we can always create a new series. So we can look at a new series called its associated series. And the series is going to be the absolute value of the terms, the sum of the absolute value of the terms. Now, this series is not the same as the other series, right? Because it takes away all the negative terms, or it turns them into positives, I should say. Okay, we don't know yet how these two series are related. We've seen something like this before when we look at absolute values in the divergence test, but we're going to be looking a little more deeply at this today. So definition. We have a special name for when this absolute value, this associated series, converges. A series is called absolutely convergent. Okay, absolutely convergent if its associated series converges. Okay? So this is a strange definition for now. We're going to see later why this definition makes sense. But for now, what we're saying is that we call this guy absolutely convergent if this other guy converges, which is a little weird, right? Because we don't even know what it means for this other guy to converge and how that relates to the original series. But we call it absolute convergence, okay? Now, I want to note something here that is important. If we're dealing with a positive series, then this series, its associated series, is actually equal to the series. So, convergence and absolute convergence mean the same thing. Okay, so, absolute convergence is not that interesting of a statement when you already have a positive series. Okay? Okay, so let's look at some examples. What about the following series? Okay. So, what if we look at its associated series? Its associated series is What is the absolute value of it? So if we were to look at the absolute value of the series, that just kills off the -1 terms, and so it ends up becoming this series. And this guy converges, doesn't it? How do we know? Because this is a p-series with p equal to 2, which is greater than 1. So what does that tell us about the original series? That the original series is absolutely convergent. Okay, this is the definition of absolute convergence, that the associated series converges. Okay, so this leads us to say, so everything down here leads us to say this statement, okay? Now, is every series that converges absolutely convergent? Well, let's take a look at this next example. So question, does this series absolutely converge? Well, let's take a look. What is its associated series? Well, I'm going to look at the absolute value of the series, or of the terms. And I end up with just 1 over n. But this series diverges. Remember, that's the harmonic series. You're allowed to just state that it diverges. We already showed that in an earlier section. So what does that mean? This implies that the series that we started with is not absolutely convergent. Okay. So we've seen an example of a series that absolutely converges. We've seen an example of a series that is not absolutely convergent. So this leads us to the next definition. A series is called conditionally convergent if let me write it this way. If the series converges but its associated series diverges. Okay, so what does this mean? This means that this guy converges and this guy diverges. That's what this means. If a series satisfies both of those properties, then we call the series conditionally convergent. Have we seen a conditionally convergent series? Yes, we already have seen one, right? So let's say note this guy remember this guy, okay? We just did this example. This guy converges, and if you look back at your notes from 11.5, we learned the alternating series test, and we actually showed that this guy converges. So this guy converges, but its absolute value diverges. Again, this is the harmonic series. So this series is conditionally convergent. Okay. So just to show you guys that these definitions are not for nothing, we have already seen a case where this happens. Okay. This leads us to an extremely important theorem. This is called, this theorem actually, this theorem is so crucial and fundamental that we're going to be using this fact all along, and it kind of goes, we're going to see why we call it absolutely convergent, okay? So let's look at this next theorem. Why do we call a series absolutely convergent just because its associated series converges? Well, this theorem will answer that question. If a series absolutely converges, then it also converges. Okay, so this makes sense now of why we call it absolutely convergent. Okay, so I want to do a proof of this, okay, because it's a nice proof. So because we're trying to prove this, we need to start with the assumption, right? We're assuming that a series absolutely converges. So I want us to suppose this guy is absolutely convergent. And let's go back to definitions, right? What does it mean for that guy to be absolutely convergent? i.e., that means that this converges. Okay? So where do we go with this proof? Well, if this guy converges, then this implies that multiplying it by 2 also converges, right? So that means that this guy also converges. I'm going to store this fact away in a second, okay? Now, notice that an, every term is always sitting between the negative of its absolute value and its absolute value. Okay, this is just a fact. You could say this about any number, right? Anything sits between the negative of its absolute value and its absolute value. Right? If it's positive, it's equal to the right term, and if it's negative, it's equal to the left term. But it always sits between them. So this is true. So what I'm going to do is I'm going to add the absolute value of an to this inequality. So this implies, this is true for all n. So this implies that 0 is less than or equal to an plus the absolute value of an, which is less than or equal to 2 times the absolute value of an. Now, why did I do this? Well, remember, we have above that this guy converges, which means this guy converges, which means by the comparison test, we could say that this guy also must converge, and that's what we need. So I'm going to say by the comparison test, this series converges. But remember, we already have that this guy converges, so now what we're going to do is subtract them. This implies that this guy minus this guy, which is equal to what? That's just equal to this guy must also converge, since it is the difference of two convergent series. And so that's the proof, right? Because we wanted to show that this guy converges. So we're done. But leave the proof out of your mind for now. The important thing is the theorem statement, okay? We're saying if a series absolutely converges, then it also converges. So now we understand that the terminology makes sense. Even though our original definition was something is absolutely convergent if its associated series converges, well, that's because of this theorem. This theorem implies that if the associated series converges, then it converges also. In other words, absolute convergence is stronger than just regular convergence. Okay? So, here's what we have learned from this. What we've learned now is that there are two choices here, right? So for any series, either it converges or it diverges. But in the world of convergent, we have absolute convergence or conditional convergence. So this means there are three choices. Either something diverges, or it conditionally converges, or it absolutely converges. These are the only three choices for any series. Now, do we need to say if something absolutely or conditionally converges? Well, if the problem just tells us and asks us whether it converges or diverges, well, you don't have to determine absolute or conditional. You could just figure out if it converges or not. Okay, but these are the three choices. There are no other choices for a series. So this kind of leads us to a new strategy. Okay, so let me just say that we now have a new strategy / trick up our sleeve. If a series has negative terms, look at this series instead. If it converges, then the theorem says our regular series must also converge. Okay, so this is really nice. It means that if a series has negative terms and we can't use the older tests on it, we can look instead at its absolute value, and if it converges, then the theorem says that AN must also converge. Now, I'm hoping you guys don't take this theorem too far, because let me just write a little warning here. Warning, the converse of the theorem is false. What do I mean? So I mean, the theorem says that this guy converges implies this guy converges. This is true. However, the following is false. This guy diverges implies this guy diverges. That is completely false. Okay, so if this guy diverges, or let me write it this way. This guy may converge or diverge. We just don't know. Okay, so in other words, this is a shortcut only if the associated series converges. Okay, let's do an example. So let's look at an example that's really going to hit this shortcut home, okay? Let's look at number 3. I want us to study the series Now, before you sit and you try to apply one of our old tests, I want you to think really carefully about this series, okay, and what the nature of the terms are. What does this series look like? So if we were to write out these terms, that's the first term. This is the second term. Oops, this would be 2 squared, right? This is the third term. This is the fourth term. This is the fifth term. And it goes on. Now, why am I doing all this? Because if you actually put your calculator in radian mode and you figure out what cosine of 1 is, this guy is positive. But if you figure out what cosine of 2 is, it's actually negative. So you might think, oh, okay, I've got an alternating series. I can use the alternating series test. But if you look at cosine of 3, it's negative. Cosine of 4 is also negative. And then if you put cosine of 5 in your calculator, you get a positive. And so what do we notice? We notice that we have this series has no pattern with its signs, right? Cosine oscillates between -1 and 1, but not periodically with the integers. And so this is going to bounce back and forth between negatives and positives. Maybe sometimes you'll have 2 positives in a row, maybe sometimes 3. But the point is that there is no distinct pattern, and it certainly isn't alternating, and it's certainly not a positive series. And so what does this mean? We cannot use any of our previous tests since the series is neither positive nor alternating. So we could never deal with a problem like this before, except now we have the theorem, and the theorem is going to be the tool that saves us here. So let's look instead at its alternating series. Sorry, it's associated series. It's associated series is, so we're going to look at the absolute value. Okay, so we're looking at cosine of n the absolute value of cosine of n over n squared. Now this may look even more difficult to you, but here's the important part. This is now a positive series. What does this mean? This means that we can now use 3 different tests on it, right? This means that we've unlocked the ability to use the integral test and both comparison tests, right? We've got the comparison test and we've got the limit comparison test. Okay, so which of these will apply? Well, I would like you to think a little bit about cosine, right? We know that cosine of n sits between -1 and 1, which isn't very helpful, but if you look at the absolute value of cosine of n, this means that it sits between 0 and 1, right? Because it can't be negative. Which means that if you divide all of those by n squared, it means that our series sits between 0 and 1 over n squared. So we're going to use the comparison test because this guy over here is easy to study. Let's look at that series. So this series converges. Why? It's a p-series with p equal to 2, which is greater than 1. So, by the comparison test, that absolute value series converges. What does this mean? This means that our original series converges. And this is true by the theorem, right? So that means this guy converges. And not only does it converge, but I just showed that it converges absolutely, right? Right? Because I showed that its associated series converges, and that's exactly what the theorem says. Let's go back. The theorem says that if a series absolutely converges, then it also converges. Okay, I hope these ideas are becoming a little more clear, but I know there's a lot of terminology here to learn. Now, the last part of this section involves us learning 2 tests. These tests are extremely important because they have to do with absolute convergence. So let's look at these 2 tests. The first test we're going to look at is called the ratio test. I usually abbreviate the ratio test like this. I use the letter A in there because there's going to be another RT. So this is going to be called the ratio test. Consider, so let this guy be a series. And suppose that the limit as n goes to infinity of an plus 1 over an equal L. Now, before I move on, I want to explain what this condition is right here. Okay, what we're doing is we're actually dividing a series, a term in a series by the term before it. Okay, so that's what we're doing. We are combining and we're seeing what we get as a limit, okay? Suppose that we get this guy L for its limit. Now, if L were to be 1, then that means that eventually the terms all start to look the same, in which case there's no way it can converge, right? Because it's not going to 0. So it depends on how small things are, but 1 appears to be the magic number, because if you're bigger than 1, then what that means is that the guy on top is essentially being multiplied by a constant. So each term is being multiplied by a constant as you go further and further out. In other words, the terms are getting bigger and bigger. And so there's no way it can converge. Or likewise, if L is smaller than 1, then that means that the terms are essentially getting multiplied by a fraction each time, and they're getting smaller and smaller. So this leads us to the conclusion. I'm not going to prove this theorem, which is why I wanted to explain a little bit about it, but these are the cases. If L is less than 1, then AN converges absolutely. And if L is greater than 1, then this guy diverges. That is all the theorem says, and you'll notice that there's no mention of what happens when L equals 1, so do not make up your own rules. There's a reason why I didn't include that. So, warning, if L equals 1, the test tells us nothing. What does this mean? This means you used the wrong test. Try again with a different test. Okay, so ratio test only tells us something when L is less than 1 or when L is greater than 1. Okay, so I would like for us to practice using this test a few times. I will say, before we do an example, I want to say a tip here. So a tip. This test works best for series which contain powers of n or factorials or both. So this is my tip of when it's best to use it. I would like to do a couple of examples to illustrate this. So let's look at number 4. We're going to study the following series. N cubed over 3 to the n. And we have a negative 1 to the n power there. So we are going to use the ratio test, okay? So using the ratio test. The ratio test says that we need to do the limit as n goes to infinity of the absolute value of an plus 1 over an. So what is this actually equal to? What's nice about the ratio test is you don't need to find another series to compare it to. You're dealing with one series the entire time. Okay, so what's the limit as n goes to infinity of this? Let's go ahead and write down what the quotient would be. Okay, what is an plus 1? we're going to have, we have the negative ones in there, but you know what? I'm not even going to write down the negative ones because we know that the negative ones are about to go away when we take the absolute value, right? It's a factor, so it's going to go away. So what do we end up with? an plus 1 is n plus 1 cubed over 3 to the n plus 1. And then we're going to multiply it by the reciprocal of an, so that's 3 to the n over n cubed. So this is what we get. And at this point, we can even erase the absolute value because we've gotten rid of all the negative stuff. So let's get rid of that. Okay? So we need to take the limit as n goes to infinity of this. So here, a lot of stuff can cancel. Well, you're going to notice that whenever we use the ratio test, lots of stuff cancels. In this problem, only a little bit does because 3 to the n over 3 to the n plus 1, we know that by the exponent rules, we're going to be left with 1, 3 at the bottom, right? So n of those are going to go away with n of those. We just have a 3 left on the bottom. So what is this equal to? This is equal to the limit as n goes to infinity of n plus 1 cubed over 3n cubed. I'm going to actually rewrite this as follows. Isn't this the same as n plus 1 over n cubed? And I'm just going to pull the 3 out because the 3 is not being cubed. So to do a limit like this, you can just divide both sides, top and bottom, by n cubed, which means inside you're dividing by n. So this is equal to the limit as n goes to infinity of 1/3 times 1 plus 1 over n over 1, all cubed. But this guy goes to 0. And so what is this limit equal to? It's just equal to, let me make this more clear. It's just equal to 1/3. And so what did we conclude? As long as you don't get 1, you're in business, okay? This is less than 1. Okay? So what do we gain from that? Remember, the ratio test says that if you get a limit that's less than 1, this implies that the series converges absolutely. Okay. Very nice, right? It's a beautiful theorem. It's a beautiful test when we have the right conditions for it. You'll notice that in this in this series, we had an n as a power. And remember I said, see this n up here as a power? This is sort of my clue that I know the ratio test is going to work well. Okay? Now, I want to demonstrate a problem with factorials because the ratio test really shines with factorials. So let's do another example. This is going to be number 5. So we're doing this series. It's going to be n to the n over n factorial. You'll notice that, remember I said that the ratio test is good for when you have powers of n or factorials or both. Here's an example of one where we have both. All right, so let's use the ratio test. We're going to do the limit as n goes to infinity of the absolute value of an plus 1 over an. Now I wrote absolute value, although you guys noticed that this was already a positive series, right? There's no negatives anywhere. Everything's positive. So this means that the absolute value is not really going to do anything. So let's go ahead and write out the terms. The n plus first term is going to be, just replace every n with an n plus 1. And then we're going to multiply it by the reciprocal. This is what we have. Okay, this might look weird, right? We've got a lot of stuff here and we want to figure out how to cancel stuff correctly, okay? Let me go ahead and deal with the n factorial and the n plus 1 factorial first. Factorials cancel really nicely with their subsequent term, right? Let me give you an example. If you have a 5 factorial, let's say, divided by a 4 factorial, 5 factorial is really 5 times 4 times 3 times 2 times 1, which is the same as 5 times 4 factorial. And the bottom is just 4 factorial, and so you're just left with 5. A factorial always does this, okay? It cancels really nicely with the previous factorial. And so if you look at n plus 1 factorial, another way to rewrite this is n plus 1 times n factorial. So if you write it like this, it should be clear that the n factorials are going to cancel and you're just left with n plus 1 on the bottom. Now what? There's so much canceling I can do here that I want to do this in steps, okay? So that's my first step. My second step, let me write what I've got. This is what I've got now. Now I look at the n plus 1s. I've got an n plus 1 to the n plus 1 on top, and I've got an n plus 1 to the first power on the bottom. So if I cancel n plus 1 things with one thing at the bottom, then I'm going to have n things left on top. So that's going to go away, and I have n things left on top. I'm hoping this makes sense. So I have the limit as n goes to infinity of n plus 1 to the n over n to the n. Now, this limit is actually tricky, okay? It might seem pretty harmless at first, but if you try to do the trick that we've been doing where you divide both by the largest power in the denominator, you actually end up with the following. You end up with the limit as n goes to infinity of 1 plus 1 over n over 1, but to the n, and the problem is that this essentially equals 1 to the infinity, which is indeterminate. In other words, we don't know what this equals. It depends on whether it goes to 1 faster than it goes to infinity, and there's a whole bunch of complicated math going on here. Okay, so how do we do a limit like this? I'm going to do this on the following page, okay? So here is the trick. The trick is going to be to do L'Hopital's rule in a special way. We can't use it yet. So I'm going to write the limit over here. We're going to do the limit. I'm going to use x's just because it's customary to use x's when we do L'Hopital's rule, okay? So we have the following. Let me make sure I write it correctly. X plus 1 over x to the x. Now the trick is to write it this way. E to the natural log of x plus 1 over x to the power of x. Now the reason we do e to the natural log is we bring this x down. Oh, I forgot to write limit here. Let me write it this way. And I could take this x and bring it down behind the ln, because that's what ln lets you do. So we have the following. So what do we do now? Well, the trick when you learn this in Calc 1, is to write it this way, right? This is really, the limit of e to the something is really e to the power of the limit as x goes to infinity of x ln of x plus 1 over x. So we're going to do this limit now separately. So if you were to write that limit down, this actually goes to infinity times the one on the right goes to 0, right? Because the inside goes to 1 and ln of 1 is 0. So the trick for these kinds of problems is to write it this way. And now this goes to 0 over 0, so we can use L'Hopital's rule. So this is equal to, by L'Hopital's rule, it's going to be the limit as x goes to infinity of, we got to take the derivative, and let's see what we get. This top guy, okay, I think I'm going to write it this way. This top guy, isn't it really the ln of 1 plus 1 over x? I think it's better to write it this way, okay? So we need to take the derivative of the top and the derivative of the bottom. So the derivative of the top is 1 over 1 plus 1 over x times the derivative of the inside is negative 1 over x squared, and the bottom is 1 over x, so its derivative is negative 1 over x squared. And so this cancels with this. So we're actually just left with the limit as x goes to infinity of 1 over 1 plus 1 over x. This guy goes to 0, and so this whole limit goes to 1. So coming back over here, this box was this box. In other words, this whole limit is equal to e to the 1, which is e. That was a lot of side work. So if we go back to our problem that we're working on, this limit is really e. Now let's think about the ratio test. That is larger than 1, isn't it? So by the ratio test, our series diverges. Very cool problem because it allowed us to practice some complicated limit taking techniques. So the last thing in this section is gonna be to go over a test that we don't use all that often, but it does come in handy when the situation arises. So the next one is called the root test. So I usually abbreviate that one ROT. So it's called the root test because it involves taking a root. So I want you to suppose, so let AN be a series. And I want this time for us to take the limit as n goes to infinity of, instead of comparing or dividing the n plus first term to the nth term, we're going to do the nth root of the absolute value of an. So I want us to suppose that this limit is L. The good news for this test is that it has the exact same conditions as the ratio test. Okay, so first, if L is less than 1, then AN converges absolutely. And if L is greater than 1, then AN diverges. Okay? I hope this goes without saying, but that is the entire test, and so of course I'm going to give you the same warning. If L equals 1, the test gives us no info. In other words, use a different test. So let me give you guys a tip for this test. Tip. The root test works best if our series is a perfect nth power. In other words, it looks like this. Okay, so I want to do a demonstration here, a couple of problems where we see the usefulness of this test. So let's look at number 6. We're going to study the series. Now, I want us to notice something. Even though it doesn't look like that form I wrote, because both of these guys are to the nth power, can't I write the series as follows? Right? So we use the root test. So what I'm going to do is I'm going to do the limit as n goes to infinity of the nth root of the absolute value of an. So that's going to be the limit as n goes to infinity of the nth root of, what's the absolute value going to do? It's just going to kill off that negative sign. So aren't I going to get as follows? Because that's all absolute value does. It turns all the negatives into positives. But what is nth root of something to the nth power? These two things cancel each other out. In other words, we just have the following limit. And this is equal to 0. Is this a good thing? Yes, it is, because it is less than 1. So by the root test, the series converges absolutely. Okay, the root test works extremely well when you have perfect nth powers. Let me do one more example. We're going to do arctan n to the nth power. Okay. What does arctan look like, by the way? Do we have to worry about this negative or positive oscillation thing here? We do not, because arctan actually looks like this, right? So, sorry, arctan, arctan looks like this. And so arctan n is just going to be dots along this, right? Okay, so we are looking also from 1 to infinity, so we're really only coming to the right of that, right? So we're only looking at those dots. So let's use this picture to guide us in a moment, okay? So we're going to use the root test because we see that this is a perfect nth power, right? So root test says we're going to do the limit as n goes to infinity of the nth root of the absolute value of this is just going to be itself. So I'm going to write this down. It's arctan n to the nth power. But again, the nth power and this nth root cancel each other out. So we're left with the limit as n goes to infinity of arctan of n. What is this limit actually equal to? Well, look at the picture, right? What happens as we go to the right? We approach pi over 2, don't we? This is equal to pi. Well, let me do this on the next line. This is equal to pi over 2. Is that larger than 1 or not? Well, do pi divided by 2 in your calculator, 3.1. We know this is going to be larger than 1, right? So we can conclude by the root test. The series diverges. I know this was a long video. Thank you for watching. We're not quite done yet. There is one last thing I want to say. I want to say be careful. The ratio test and root test are sort of like sister tests, okay? What do I mean by this? I mean, if one works, the other does. But more importantly, if one gives no info, the other one will also give no info. This is important. This means that if you are doing, let's say, the ratio test, and you get L equals 1, which means no info, try a different test. Other than the root test, right? Because if you try the root test, you're wasting your time. It's also going to give you no info. The L that you get will also be 1. So this is just my way of saying don't waste your time trying things that you know in advance are not going to work. If the ratio test doesn't work, then neither will the root test. Okay? Thank you very much for watching, guys. Good luck.